also talk about the choice of coordinate system that we will use in the analysis later. This particular choice of coordinate system is chosen to simplify the calculation. Okay, I choose the origin of the coordinate system at the centroid of the cross section at the left end of the body. Okay, and also x3 is chosen to direct along the axis of the cylinder. Okay, so x3 pointing in this direction. x1 and x2, I chose them to direct along the principal axis of the cross section. Okay, so last time I showed you the properties like this. Okay, because the origin O here is chosen at the centroid of the cross section, so the integral of the coordinate x1 and x2 across any section will be 0, right? Okay, because the origin is at the centroid. So from the definition of the centroid, you can easily prove that the integral of x1 or integral of x2 across the section is a 0. Okay, and also we assume that x1 and x2 direct along the principal axis, so the product moment of inertia have to be 0. So that term or that property we got from the choice of x1 and x2 that direct along the principal axis. Okay, if you choose arbitrary direction of x1 and x2, that one may not be true. Okay, the product moment of inertia here can be non-zero. Okay, I also define I1, I2, and also J, right? So that should be the quantity that you are familiar with when you learn about beam theory. Okay, so basically I define the moment of inertia about the axis x2 and x1 like this. So if you want to compute I2, you just simply take the integral of the coordinate x1 squared, okay, across the section, so you get I2. The same way for I1. Okay, for the polar moment of inertia of the cross section can be obtained in the same manner. So we take the sum of I1 and I2, or you can just simply go back to the original definition of J. Okay, so I1 and I2 here are used in the calculation of bending stress due to bending moment. If you remember, if you try to get the distribution of stress across the section due to the applied moment, you can use this kind of property, okay, to distribute stress across the section. And also when you look at the torsion problem, okay, shear stress can be obtained at any point in the cross section, and that should be related somehow to J. Okay. Now look at the loading conditions for the special class problem that we are interested in here. I assume that the body force vanishes at every point. Okay, so the problem that we focus on here, there's no body force. Okay, B is identically 0. Okay, at every point. How about the boundary conditions? Okay, we have 3 boundaries here, right? We have the surface SL, the surface SR, and also the side face S pi, right? So let's focus on this kind of special cases. Okay, so we look at the PL traction boundary value problems. Okay, so at every point on the boundary, we know tractions completely. Okay, So in this particular case, we can say that SU, the surface SU, is simply the empty set. Okay, and the ST is simply the entire boundary of the body. Okay, so there is no point. There is no point on the boundary that we know the displacement. So we know the traction completely at every point on the boundary. Okay, this is the boundary condition that we will focus on. Okay, so on the side face, we also have you know, the information like this. So the traction vanishes at every point on the side face. So at every point on the surface S pi, we will not apply any traction, or we can say that we apply the traction equal to 0. So T is 0 at every point on the surface S pi. Okay. How about on the boundary S1, SL and SR? At the left end of the body, so we apply the traction. Okay, we apply the traction. Let's say that, okay, the traction at any point on the surface SL is prescribed equal to T0L. T0L here is a function. It's a given function. Okay, it's a given function of the coordinate at any point of this cross section SL. Okay, the same thing here for the surface SR. We specify the traction at every point. Okay, so T is simply T0R. Okay, and T0R here is a given function, okay, of X at the on the surface SR. Okay, so this is the boundary conditions that we will focus on. Okay. Because the problem that we look at here, we don't have this, we don't have the displacement boundary conditions. So we specify the loading condition and also the traction boundary condition. So in this particular case, we need to make sure that they apply loading condition. Okay, they apply loading condition and also the boundary condition. They are consistent. Okay, the traction that apply at every point on the boundary and also the body force field have to be in equilibrium. Okay, because we don't have any way to restrain the body. We don't have any way to provide the reactive force to the system, right? Because there is no point on the boundary that we know the displacement. In this particular case, there is no reactive force that can provide, you know, can provide the unknown force to satisfy equilibrium. So we need to make sure that the traction that provide at every point on the boundary must be in equilibrium because the body force field is 0. So what I try to say here, T0L and T0R cannot be independent. They have to satisfy this condition. The condition that I just mentioned here is simply equilibrium of forces, right? So if you combine all the forces that apply to the body, okay, so we have what? Body force field, right? The body force field is 0. Okay, and T is 0 on the surface S pi, and also we have T0L and T0R here. So the sum of all forces, the sum of all net forces have to be 0. So I just simply take the integral of T0 over the cross section at SL. So this produces the net force at the left end. Okay, and this one is simply the net force at the right end. The net force on the side face and the net force from the body force are 0. So now the combination of the net force from the left and right end have to satisfy that equation. Okay, so if this equation is not satisfied, we can say that, okay, the body is not equilibrium. It's not in equilibrium, right? So if the net force is non-zero, so now the body will undergo the motion, right? we will have the acceleration. And that particular case is not of interest here. So we just simply look at the case that the body is in the static equilibrium. Okay. And also we need moment equilibrium as well. So when you take the moment, the net moment of all forces that apply to this body have to be zero as well. Okay, so if I take the reference point at the origin and I form the moment due to the applied tractions about that point, I will get these quantities, and this quantity have to be zero. So the integral of R cos T0L here represent the net moment at any point, the net moment at any point on the cross section at the left end, and this represent the net moment about the point O for the traction applied at the right end. Okay, the combination of the two have to be zero. Okay, these two conditions have to be satisfied. Okay, if one of them or both of them are not satisfied, now the body is under, and the body here undergoes the motion, and we will have the acceleration. Okay, and that is not the case that we are interested in. Okay, we need to make sure that before we solve the problem, we need to check that okay, the left end traction and right end traction satisfy the two conditions here. Okay. Now let's make some assumption here. Okay, we will try to impose some of the spatial condition or spatial situation like this. So let's assume that okay, the length of the body, the length of the cylinder here, or L here, is sufficiently large. Okay, in comparison with what? With the dimension of the cross section. Let's say that okay, you have the characteristic dimension of the cross section. You can think about the smallest circle that can enclose the cross section, and we can use the diameter of that circle to measure the dimension of the cross section. Okay, let's say that okay, L here is much larger than the dimension of the cross section. Okay, just focus only on this particular case. Okay, so if this is the case, if L is much larger than the size of the cross section, so there exists an interior zone. Okay, an interior zone that away from the end zones, because if L here is much larger than the size of the size of the cross section, so the interior zone exists. Okay, I'm not sure that is clear to you. SR, there's a question from your friend. SR is right side. Yeah, that's right, because the right end, SR is simply the right end. That is right. Do you have any concern about that? Fam? I don't understand your question. So you confused about the symbol or what? Can you explain about the question that you asked me here? Okay, can you use microphone? I don't know. You said that SL is right side. That is, it should be clear from the figure, right?
I mean the previous line. Please.
Okay. What is there any typo there or anything that wrong in the slide?
Yeah, previous slide. Yeah, left and SL and
Okay,
right
okay,
end.
and yeah, you're right. Okay, this is typo. Okay, so just simply change this to the right end. So this is not the left end. This is the right end. Okay, so
Yeah.
that's the mistake. Okay.
Yeah.
Okay. So now we assume the length of the body, okay, to be sufficiently large. So in that case, we can say that there exists the interior zone, okay, that far away from the end zone, okay. And if the solution that we are interested in is the solution at the interior zone, so let's think about that. Okay, we have very long body, okay, and we don't care much about the solution at both ends or the region close to the ends. We just simply focus on the solution in the interior zone. Okay, so if we face with this situation, what can we do to simplify the problem? Okay, we look at the body that's very long. Okay, compare with the cross section dimension. So and we are interested in only the solution in the interior zone. The interior zone, I talk about that zone. Okay, I don't care about the zone close to the end. Okay, so the interior zone here exists if the body the length of the body is sufficiently large, right? Okay, so if we are interested in this interior zone, okay, the solution at any point inside the interior zone. So we should be able to simplify the problem that we considered before, right? Because we apply the loading condition only at both ends, right? So we apply zero body force, and we don't have any applied loading on the side face. So the loading condition is applied to the body at the left and at the right end. What happens if we don't care much about the solution close to the end? And also the interior zone here exists. Okay, and we look at the solution inside this zone. What can we do to simplify the problem here? You think? Is there any way to simplify the problem? So now we come up with this principle. So Saint-Venant proved this principle long time ago. Okay, so and this was very useful. And then you apply this kind of principle before in the strength of material class in your undergraduate study, right? Because when you think about the beam or even the axial bar, okay, for example, the truss element in the truss structure, okay. So if you don't care much about the connection at both ends of the truss member, you can assume that, okay, inside the interior zone, that far away from the end, think about the truss structure. You learned about that kind of structure before, right? Okay, let's say that, okay, this is the truss. Okay, so you have the structure like this, and you have apply force somewhere at the nodal point. Okay, this is the joint of the truss. Okay, so you know that, okay, each member, each element here connect to each other at the end by means of the connection, like a bolt connection or even the welding connection. So if you apply the force like this, and if you focus only on the interior zone of each element, you can assume that the state of stress at any point inside thrust element, the state of stress is uniform, right? So we assume that, okay, at every point here, you will see exactly the same thing. And the member is purely axial member, right? So that is correct only for the interior zone, right? Because the behavior will be more complicated, much more complicated when you look at the end zone of the elements, because you have the detail of a connection. You have a complicated manner of the distribution of the force from, to that element. Because if you look at the force that apply here, the force here will distribute to each element due to the stiffness of the member and also the equilibrium of the joints. So the force there will distribute to each element. The distribution will be very complex if you look at the joint, because it depends on how you connect the element together. And you have the detail, like, for let's say, okay, if you have the bolt connections, so you have complicated detail at the end of each element. You may have several holes that you drill there to and put the ball there to transfer the force. So the distribution of stress across the section is very complicated in the region close to the end. But if the length of the member here is sufficiently large compared with the size of the cross section, now you can simplify the field inside, the field in the interior zone. If you don't care much about the field at the interior zone, now you can say that for this particular case, stress should be uniform at any point in the cross section, right? For when you move far away from the end. That is somehow related to the Saint-Venant principle. Okay, you apply that before a long time ago when you learn when you learn mechanics of material class, right, or the strength material class. Okay, so Saint-Venant proved this principle, but I will not prove it here. Okay, if you would like to get the proof of the theorem, so you can go back and do the search, or you can look at the textbook, the classical textbooks. You can find the proof of principle of Saint-Venant. The proof will not be very simple. Okay, it's not simple because you need to deal with some mathematics. So that's the reason why I will not show you the proof here. Okay, let's look at the principle. Okay, let's say that, okay, we have the length of the body sufficiently large compared with the dimension of the cross section. So Saint-Venant just say that, okay, the solution inside the interior zone, the far away from both ends, depends only on the resultant force and moment. Okay, it just simply dependent on the resultants of the traction that you apply at both ends, not how they distribute. Okay, so the distribution of the traction or the function that provide the distribution of the traction at both ends are not important. Okay, so and that kind of information, okay, is less and less important when you move far away from the end. Or I can say that the dependence of the solution, on the distribution of the traction at both ends start to decay more and more when you move far away from the end. Okay, is that clear? So if you look at the principle in this way, it means what? So if I try to apply the traction at both ends of the bar that produce exactly the same net force and net moments, okay, but I use different kind of traction, different kind of distribution. But let's say that, okay, that distribution or that traction produce exactly the same net force and moments. So if you look at that two particular cases, when you move far away from the end, you look at solution in the interior zone. Okay, the two cases will give you about the same solution. Okay, in the interior zone. That is based on the principle, the Sengbernon principle. So the detail of the distribution at both ends is not that important. If you focus only on the solution in the interior zone that far away from the end zone. Okay, I'm not sure that is clear to you. So if it's not clear, so look at this problem. Okay, let's say that, okay, I have a long body. Okay, the L here is sufficiently large compared with the dimension of the cross section. So let's say that, okay, I have D here to represent the size of the cross section. You can think about the smallest angle, the smallest circle that can, you know, enclose the cross section like this. This is smallest circle. Okay, so let's use D here, the diameter of the circle, to measure the size of the cross section. So let's say that L here is sufficiently large compared with D. Okay, and look at this kind of loading condition. I look at the simple loading condition first. Okay, let's say that, okay, at the left end and at the right end is subjected to the uniform normal traction. Okay, and that uniform normal traction produce the net force equal to P. Okay, there is no net moment for this particular case, because if you look at the net moment about the origin, okay, so the net moment will be 0 because the loading that you apply here is uniform, and you choose the origin at the centroid of the cross section. So in this particular case, the net moments computed at the origin is 0. Okay, so in this case we have only the net force, and the net force direct along x3 and negative x3 direction, right? Okay, so this is very simple loading condition. Okay, let's say that, okay, this is the first problem that we are interested in. Now look at the second case. I look at the same body, but now I just simply change what? The loading condition at the end. I still look at the not uniform, not uniform. I still look at the normal traction applied at both ends. I look at the traction that is not uniform here. You can think about the parabolic distribution, for example. Let's say that, okay, this distribution also provide the same net force and moments. Let's say that the net moment is 0. So we apply the traction here in a way that, okay, the moment about the origin is 0, and the net force is simply equal to P. Okay, exactly the same P that we consider for the first problem. Okay, and look at this problem, and we say we have the second different problem here, right? So I call this Bari value problem 2. So these two problems are different. Okay. Now look at the third one. Okay, I look at the same body, just simply change loading condition at the ends again. Okay, here I still look at the body subjected to the normal traction at both ends, but it's not uniform. But the distribution here is different from the second problem. Okay. Let's say that, okay, the distribution of the traction that I look at here also produce 0 net moment about the origin. Okay, and also produce the same net force again. And let's set this problem number 3. Okay, I look at 3 different loading conditions. The same body, the same long body. Okay, but we apply different distribution of the traction at both ends. But the 3 here have some common feature, that the net force is the same, equal to P, but the net moment is 0. Okay, now what can I conclude from Sengbernon principle for this particular 3 problems? Can you tell me? So if we look at the Sengbernon principle, let's say that, okay, we have this kind of situation. The length of the body here is sufficiently large compared with D. Okay, so L here is much larger than D. how much that I said the wording like sufficiently large. What do I mean by that? I just simply said, okay, L here, when you take away the end zone, you still have the interior zone left. Let's say that, okay, I said that, okay, we move far away from the end zone, far away in the sense that the distance from the point that you consider to the end of the bar is at least 2 to 3 times of the size of the dimension. So now if you move far away from the end with the distance larger than or equal to 2 to 3 times of the size of the cross section, now we can say that we is far away. We are far away from the end zone. Okay, so let's think about that. Okay, the size of the end zone here is about 3 times of the d. Okay, so now if the length is larger than 6 times d, now we can say that the length of the body here is sufficiently large, because we will have the interior zone left here in the central region, right? Okay, so for this particular case, the length L here have to be larger than 6 times d. Okay, so if that is the case, we have the interior zone exist here, right? Okay, so that's what we call the interior zone. Now let's say that, okay, if we are interested in solution in the interior zone, like stress or displacement field, strain field, okay, if we are interested in the region here, okay, we are interested in the solution in this region. Saint-Bernard principle just tell you that if you don't care much about the solution at the end zones, the solution in the interior zone doesn't depend on how the traction distributes at the ends, but it depends on the net force and moment, because the 3 problem that we look at here, okay, even though the net force and moment are the same, but the distribution are different, right? Okay, so if we don't care about the end zone, the solution inside here are about the same, right? I'm not sure that it's clear. Is that clear to you? Okay, so Saint-Bernard principle allow you to solve these 3 problems, okay, in the same way, if you don't care about the end zone. I didn't say that the 3 problems will give you exactly the same solutions. Okay, at least when you move close to the end of the bar, you will see different solutions for sure, right? Because the detail of the traction that you apply here are different. So when you move closer and closer to the end, both ends of the body, you will see you will see different fields. Okay, because you cannot get the same field, exactly the same field, because if they are exactly the same, how can they satisfy the different distribution of traction? So that should be clear to you, right? So the solution for the 3 problems here are different for sure, at least at the end. But inside here, I didn't say that the solution are exactly the same, but the difference of the solution for each case is here, for each case that we consider here, is very minor. Okay, the difference is insignificant if you look at the zone that we call the interior zone here. So the detail of the distribution of the traction start to decay more and more and faster when you move far away from the end zone. Okay, so I can conclude here, for all 3 problems, the solution inside are about the same. Okay, are about the same. Now, if we want to solve the problem and we are interested in only the end zone and the length of the body is sufficiently large, Now I can simplify the boundary value problem from what I have above, okay, to a simplified one like this. I look at the same body, but now I just simply replace the detail of the loading that I have. I just replace that by the net force and net moment. Okay, so this is what I call the simplified boundary value problem. I don't care about the distribution of traction at both ends anymore. I just simply replace the distribution there by the resultants. Okay, for this particular case, we don't have the moment resultants. Okay, we just simply have the force resultants, and that's simply equal to P. Okay, so this is the simplified problem that I talk about. Do you have any question about anything here? So later, I will not solve each BVP that I have above here. Okay, I will not solve them. I will solve the one below. Okay, I will try to satisfy the end condition, not in terms of the traction distribution, but in terms of the net force and moments. Okay. And once I solve this problem, I get a solution of the simplified BVP. I can use the solution inside the intermediate zone to approximate or to be the good approximation of the solution in the intermediate zone of each problem above. Okay, I can use the solution here that I got to describe the solution for this problem and that problem and that problem. Okay. However, the problem that the solution that I got from the simplified problem cannot be used to describe the solution of above three problem at the end zones. So if you compare the result for the end zone for this problem and that problem, they can be very different because of the detail of the traction here are different. Okay, and I don't care the detail when I try to solve the simplified problem. So you cannot expect to get the same answer, or you cannot expect that, okay, the solution at the end zone for the simplified problem can be the good approximation of the problem that I look at above. The only thing that I can use is simply the one sit in the interior zone. Okay, is that clear to you? Okay. If you don't have any question about this, let me move on to this one. Okay. Because I have to replace the detail of the traction by the net force and net moments. So I need to have a way to convert the prescribed traction that we have at the left end and at the right end. Okay, we need to transform that or convert that to the net force and moments. Okay, so this is the way to convert or to compute the net force and moments at the left end. The net force can be obtained easily by simply take the integral of the traction, each component of the traction that we have with respect to the the coordinate of the cross section. So basically, I take the integral of T10L, T20L, and T30L, okay, across the section at the left end. So that just simply the components of the net force at the left end. I call that F10L, F20L, and F30L. So they represent the components of the net force, okay, at the left end. Okay, you just simply take the integral of the applied traction or the given traction across the section, that's all, okay? For the net moments, okay, I can do in the same way. Okay, I just simply take the cross product between the position vector and the applied traction, and take the integral of that quantities across a section. Okay. So this the simple definition, right? The definition of the moment. Okay, right? You just simply take the cross product between the position vector and the traction, and so this is simply the moment of the traction. And then if you want to get the net moment, you just simply take the integral of that quantity across section. Okay, so when I expand the cross product here, I simply what? I simply the distance on the position vector measure from the origin. Okay, so I here is simply for the left end. Okay, we know that I is what? The coordinate of the position vector. Okay, at any point on the cross section at the left end is simply x1, right? It's simply x1 and x2, right? And 0, right? Because we put the origin at the left end. So that is simply R for our case, right? You just simply form the cross product with the traction, okay? And then you finally obtain like this. That is the final expression. You just simply perform the calculation like this. Now you get the components of the net moments at the left end. Okay, so if I give you any kind of traction at the left end, you should be able to compute the net force and net moment at that cross section. Okay, using the formula that I gave you here. Okay, we can do exactly the same way for the right end, right? Okay, so at the right end we can get the net force and net moment as well. Okay, so I'll get something like this. If you look at the formula that we have here, they are exactly the same, right? Right? We just simply replace the components. Okay, if you look at the formula for the left end, if you replace the component of the traction at the left end by those for the right end, you get exactly the same expression, right? Okay. And R here and R here are a little bit different, right? Because you put the origin at the left end. So now what is R then for the right end? R here is simply what? It's simply x1, right? Okay, and x2 and L, right? Okay, that is simply the position vector for point on the surface SR. But L there will not involve in the calculation. You can try when you try to take the cross product between this vector and the traction at the right end. Okay, so you will get the net moment exactly in the same form as what we have for the left end. Okay, so this is the formula that we use to convert the prescribed traction into the net force and moments. Okay. Okay, your friend just asked me about the minus sign for the M2 for the second component of the net moment. Why we get the minus sign here? Okay. Also, we also have the minus sign here if you look at the third component carefully, and that came from the cross product. Do you know how to perform the cross product, right? You can go back and try to get this formula. It may not be it may not be that clear if you didn't do the calculation of the dot product here the cross product here directly. Go back, okay, and try to perform the calculation of the cross product. You will see the minus sign here and there, okay. Or if you think about this, if you have, let's say, okay, if you have the traction in the third direction, and you try to compute the moment about x2 direction, you can get the sense of the minus sign here, because if you apply the positive T30L, okay, to the cross section, and then you multiply by x1, that will produce the moment in the negative x2 direction, right? Is that right? I'm not sure that it's clear to you. Let's say that, okay, you look at that point. So at that point, you have the positive x1, right? If you apply the traction in x3 direction in a positive sense like this, okay, that is T30L, right? So if you apply T30L in the positive x1 direction, and you look at the moment at the application point here, so let's say that this x1 is positive, right? That is a positive x1. Is that right? So if you apply the traction at that point in the positive direction, you can see clearly that this traction produce the moment in the negative x2 direction. Is that right? And
yes, done.
Okay. So you can think about that in the same way. Why we have the positive sign here? So if you think about the same point here, okay, look at the same point here, or look at the, let's say, let's think about that just a second. Maybe you look at this point. Okay, if you think about the moment of T30L, again, so let's say that this T30L applying at that point, okay, and that will produce the moment about x1 direction, right? Because x2 here is positive, right? And if this one is positive too, that will produce the moment about positive x1 direction. Okay, you can see that, right? So that's the reason why we have the negative sign here. So I try to explain you based on your, the common sense of the size or of the direction of the moment produced by applied force. But if it's still not clear to you, you can go back and perform the cross product here. You will come up with the negative side directly, okay? And also the negative side here. Okay, be careful about that negative side as well. Okay. So now I provide you here the formula that allow you to convert the prescribed traction at the left and at the right end into what? Into the net force and net moment components. Okay. The reason that we have to do in this way, the reason that we have to do this, because we try to solve the problem using principle of Saint-Bernard, because Saint-Bernard don't care much about the distribution of the traction at both ends. Okay, we care about the net force and moments. Later, when we try to solve the problem, we will replace the information of the traction at both ends by the set of net force and net moment components like what we got here. Okay, so we replace the traction at the left end by 6 components of the net force and moments. Okay, and we replace the traction at the right end by 6 components of the force and moments, 3 for the force and 3 for the moment. Okay, Is that clear to you? Okay. Now look at the stress that generated inside. Because before, if you remember, if we have the prescribed traction at both ends, if you want to confirm that stress is the right candidate of the solution, you need to make sure that stress that you got here inside have to satisfy the boundary condition. So for this particular case, we know the traction at both ends here, right? So if you take stress that you got there to the point on the boundary, and then you multiply by n, you will get what? You will get traction generated by this stress, right? And if the body, here is in equilibrium, so traction generated by stress at point on the boundary have to be the same as the traction that prescribed. Okay, that is a typical way that we do, right? When we try to verify the stress field as a solution of the problem, we need to make sure that traction generated by stress field here is exactly the same as the traction at the prescribed traction. But I told you before that, okay, we will not solve the problem by using the information of the traction at the left and at the right end. We will replace, right? We will replace the traction by the net force and moment. So now if you want to verify the condition at the left end and at the right end, you will not verify through the traction generated by stress, but you will verify through the net force and net moments generated by that stress field. So here we will do exactly the same way as what we did in the previous slide. We will convert traction generated by this stress field, okay, into the net force and moments again, okay? So if we look at the left end, we can generate the traction first. The traction at the left end can be obtained easily by simply what? We convert stress here to the traction at the left end by simply multiply stress here by NL. Let's say that NL here is an outward unit normal vector to the left end, right? So NL is simply 0, 0, minus 1, right? This is the property of the, the cylinder. So the cross section here is just simply normal to X3 axis. So NL is simply 0, 0, minus 1, right? So I can now generate traction due to stress. You have to be careful. Traction that I talk about here is not TL0, okay? So TL here is not TL0. TL0 is the one that prescribed at the beginning. But TL here is the traction generated by stress that you got somehow in the solution process here, okay? So TL here is the traction generated by sigma. We can get that easily by simply multiply sigma by NL. So finally, we get something like this, okay? We can get TL in terms of the component of stress sigma. So we get like this. The negative side that we have here came directly from the negative side of the NL, okay? Once you get TL, if you want to compute the net force and net moments of TL, it's very simple, right? So we will use the formula that we got before and plug this thing in, okay? Because I already provide the formula to convert traction into net force and moments, right? I will use that formula to convert this traction generated by stress field into net forces and moments as well, okay? So this is the net force that I will get. And also then, okay, I use the similar symbol, but without 0 for the superscript. if you compare, before I would use F1, F2, F3, 0L, but here I just simply ignore 0 to emphasize that this is not the prescribed quantities. They are associated with the traction from the straight field. Okay, so F1L, F2L, F3L can be computed easily by replacing the traction in the formula that I gave you before by the traction here. Okay, so finally I get something like this. Okay, so if you take a look at the final expression that I got here, it's exactly the same as the expression that I got before, except that we replaced T10L by minus sigma 13, T20L by minus sigma 23, and so on. So this is the final expression. So if you look at the expression that we got here, if you know straight field here, if you want to compute the net forces and moments due to that stress at the left end, we just simply plug in the value of the component of stresses, right, into this expression, and then you perform the integration across the section. Now you come up with the net force. Okay. Is that clear to you? I can do exactly the same way for the net moments. Okay, we can compute the net moments due to the straight field. Okay, we just simply again replacing traction that we got in the formula before by the traction that I have here. Okay, so now this is what we have. Okay, so if you take a look at that formula, it's exactly the same as what we have before in the previous slide, except that I replaced T with the superscript 0 by the one without 0. Okay, and we know that T1L, T2L, T3L simply like this. So I just plug it in here. Finally, I end up with, you know, the expression like this in terms of straight components. Okay. So here, the expression here and there allow you to convert stress that we got somehow from the solution technique into the net force and moments at the left end. Okay. I can do exactly the same way for the right end. Okay. The thing that changed for the right end, you have to be careful too, is a negative side of unit normal vector disappear, right? So compare with the previous case. So now NR is simply 0, 0, 1. So now I can generate traction at the right end like this without the negative side. Okay, this is the only difference that we have compared with the left end. Okay, the formula will be a little bit different, you know, in terms of the sign. Okay, so now I I can use the same formula that I got before. So now I end up with the formula for the net forces and moments like this. Okay. If you compare the expression that you got for the right end, for example, for the net forces, you can see that the expression are similar, right? The only difference is the negative side. In this expression at the right end, you don't have the negative side here, okay? Because the unit normal vector is pointing in the positive x3 direction. Also for the MR, if you compare with ML that you got from the previous slide, you can see that we switch the side, right? Okay, before we have the negative side here and positive side here, so now we switch. And also if you look at the last term, so before we have the negative side here and the positive side there. Okay, So again, the negative side, the switch of the negative side is due to the property of outward unit normal vector at the right end. Okay, so I provide you the formula to convert stress into what? Into net forces and moments. Why I have to do it this way? Why I have to compute this kind of quantities? Because we're gonna use the Saint-Vernon principle to solve the problem. Saint-Vernon principle allow us to verify the condition at the left and at the right end in terms of the net forces and moments. We hope that doing in this way is simpler in terms of solution procedure. Because if you try to force stress to satisfy the traction at every point at the left and at the right ends, that is not a simple thing to do, right? Because whenever the traction applied at both ends are complicated, guessing stress to satisfy the boundary condition at both ends may not be an easy task, right? So here we try to simplify things. If the body is long enough, we have the interior zone, and we don't care much about the solution at the end zone. If that is the case, Saint-Vernon principle allow us to change that original boundary value problem to the simplified one. And we just simply deal with the net forces and moments at both ends instead of dealing with the traction directly. Okay, so that's the reason why I have to be able to convert stress and also the prescribed traction at both ends into net forces and moments. Okay. Now let's look at the comparison of the original BVP and the simplified BVPs. Okay, I try to emphasize you here again about the two different problems. So let's say that this is the original boundary value problem. Okay, if we look at this body, the cylindrical body, we apply the traction at the left end equal to T0L and apply the traction at the right end equal to T0R, and the traction equal to 0 at the side face, and I don't have body force field. Okay, so this is the original boundary value problem formulated in terms of all quantities. Okay, this is the option one, right? So I formulate the problem in terms of the displacement, in terms of strain, in terms of stress. I forgot to remove that one, right? Because for the problem that we are interested in here, we don't have the body force field, so B should be 0. Okay, so that disappears. Okay, so this is the governing equation, and this is the boundary condition. Because for this particular case, we have only the traction boundary condition. We don't have the displacement strain anywhere, right? Okay, so this is a complete original boundary value problem. I will look at, if you look at the boundary condition here, okay, it seems simple, right? Right. It seems simple in form. Is that right? But when you go to the solution procedure, you try to think about the solution of the problem. You try to guess the form of the solution. So let's say that stress that you guess here have to satisfy all this condition. Satisfying the 0 traction condition at the side face may not be difficult, but to satisfy that condition, and that condition may not be an easy task if the distribution of traction at the left and at the right end are complicated. Okay, if the traction that are given here are very complicated. Okay, guessing stress to satisfy that condition is not the easy task. You know what I mean, right? So solving this problem may not be very simple if the information of the traction that you have here is very complicated. You know what I mean, right? Okay, let's say that, okay, the traction they apply here is not uniform. Okay, it's non-linear somehow. So how can we deal with that? How can we come up with stress, satisfy that kind of complex condition at every point? Don't forget that, okay, this have to be satisfied at every point on the surface SL and SR. You have to satisfy that condition strongly at every point, okay? So solving this original boundary value problem for complicated traction seems impossible if you use the technique like inward technique. Now, how can I simplify the problem? How can I simplify the boundary value problem that I got here? Now, if I supply the problem here with the assumption like L is sufficiently large, okay? I assume that, okay, L here is sufficiently large, and I don't care much about the solution at the end zone. I just simply focus on the solution in the interior zone, if that is my interest. Now I can change or simplify the boundary value problem that I have here to the one that's simpler. Okay. So that's what I call the simplified boundary value problem. Okay. How can I simplify this? I just look at the same problem, the same kind of formulation that I have here can be changed a bit by simply replace the condition at the left and at the right end using the principle of Saint-Vernon, because Saint-Vernon just say that, okay, if you don't care much about the result at both ends or at the end zones, you care about the solution in the interior zone. The solution in that interior zone depends weakly on the distribution of the traction. This simply dependent on the net force and moments. Okay, so based on the assumption that the length here is very large, okay, and we are interested in only the solution in the interior zone. Now we can replace the original boundary value problem by the simplified one like this. If you compare the formulation, the two formulations, so you can see that they are almost the same, except the thing that changed is the condition at the left end and the condition at the right end, right? You change that one to this one. Okay, you change that one to that one. The rest is the same. Okay, so what does it mean? The simplified boundary value problem here, we just solve the same problem, but we modify the condition at the left end, at the right end. Instead of satisfy the traction, the prescribed traction at every point. Now we just say that, okay, stress that we have from the solution procedure, we don't require that stress have to satisfy that kind of condition at every point anymore. We just say that, okay, the stress field that generated inside here, when you take to the battery, that stress field have to produce the same net force and net moment as those from the prescribed tractions. Is that clear? So we will not look at stress that satisfy this condition at every point. But now we try to convert stress into net forces and moments. And we convert traction here to net forces and moments. And then we expect to see the same net forces and moments from the two quantities. Stress and traction have to generate the same net force and moments. Okay, so that are conditions that we use here in the simplified boundary value problems. Okay, we expect that solving the problem using this simplified condition at the left and at the right end, okay, should be simpler. Easier to get the solution, okay? It should be easier to get the solution for the simplified boundary value problem, okay? So because the reason is simpler, because even though that one is very complicated, but you just simply compute the net forces and moments, and we just simply enforce that condition instead of the complex traction distribution, okay? Is that clear to you?มีใครมีคำถามอะไรไหมครับ Okay. Okay, if you look at the picture here. So if you want to solve the problem, the original problem, using the simplified version of the boundary value problem, the first thing that you have to do, you have to convert T0L and T0R into the net forces, net moments, and use that kind of information in the formulation. So this is the must. You need to get this quantities and that quantities, okay, before you can solve the problem. Okay, I will show you 3 different problems, 3 basic problems that you learned before in strength of material class. I will try to revisit the problem that you solved before. The first problem that I focus on here is like truss member. Okay, we look at the uniaxial tension problem. We look at a bar that's subjected to some kind of traction that produce only the net force in x3 direction. Okay, so we look at this particular body, okay, with the prescribed traction at the left end and at the right end. Somehow that we have very simple net force and moment. Okay, let's say that, okay, the cylindrical body that we focused on here have the arbitrary cross section. Okay, and the traction that we look at the left end, at the right end, satisfy some of the condition here. So the traction that we look at the left end is arbitrary, but it generates the net force equal to 0, 0 minus P, and 0 net moments in all direction. Okay, and the traction that we have here can be replaced by the net force P in the negative x3 direction. Okay, we just simply focus only on that kind of traction. Okay, so there is no net force in x2 and in x3 direction. There is no net moments as well in all directions. We have only the net force in negative x3 direction. We can think about this as a tension force. Okay, that is a tension force apply normal to the cross section at the left end. We can think in that way, but you know that in reality, there is no. We cannot apply the net force directly, right? Typically, we apply the force in terms of the distributed traction, right? We cannot apply the point force directly to the cross section here. We apply in terms of the distributed traction. Okay, this is simply the representation of the net force of that traction. Okay, at the right end, we apply T0L in arbitrary manner, but we need the net force equal to 0, 0, and P, and net moment equal to 0, 0, and L, 0, 0, and 0. Okay, so in this case, we can replace the traction applied at the right end by a point force. The net force equal to P, acting normal to the cross section at the right end. Okay, So this is the simple problem that I try to solve. Okay, we solved it before, right? If you remember, if you have a bar, you can think about an element in the truss structure, right? If you take one element from the truss, now you know that, okay, that element is subjected to the axial force. It can be in tension or in compression, depending on the traction that generated at both ends. This kind of problem you solved it before, right? From the basic class of strength of material, right? Is that right? So you know the answer for this problem, right? If I ask you about stress at any point inside in the view of strength of material class, you know that, okay, stress should be P over A, right? Right? If you apply the axial force like this at both ends, you say that, okay, there's no shear stress inside. The only thing that we have is the normal stress, and the normal stress that we got there, we just simply assume that the normal stress is simply uniform, right? The normal stress is simply uniform across the section. At every point in the cross section, the normal stress is the same, right? Equal to P over A, if A is the area of the cross section. That is a very simple formula that you learn from strength of material class. Okay, but here we will revisit this problem again with the sense of solid mechanics. So now you can see that the net force at both ends that we call P here actually is not the one that you apply directly to the body, right? Actually, forces that transfer or apply to the ends of the body is in terms of the traction, right? It's in terms of T0L and T0R. That traction can be very complicated depending on how you connect the body here to the other part of the structure. If you think about this is the part of the truss structure. At the end, you make the hole, for example, the holes, and you connect connect this part, this element to the other part using bolts or welding. Is it depends on the type of connection. So the distribution of the force at the end can be very complicated, or the function of T0L and T0R may be very complicated. But here, we will look at this problem. We look at this problem in the sense of simplify BVP. Okay, if the body here have the length that is sufficiently large, and I don't care about the end effect here. I look only at the solution at interior zone. Now I can change T0L and T0R to the net force moment, right? And for this case, I just focus only on the T0L and T0R that generated this simple net force moments that we call the uniaxial tension. Okay. How can we solve this problem? Now we already simplify the traction into the net force and moments. How can we solve this problem? I will solve this problem using the technique that I used before in the previous lecture. Okay, I will not solve the equation directly. Okay, if you go back and look at the simplified BVP, if you want to confirm or if you want to get the solution of the problem, you need to solve governing equation and verify the boundary condition. Solving governing equation is not easy job, right? So I will try to avoid doing that in this class. I will try to apply the inward technique, okay, by guessing the form of the solution and verify the satisfaction of the governing equation inside, and then check the boundary condition. Similar to your homework assignment. Okay, I will use that kind of technique to get the solution here. Okay, because I think about this problem simple enough, right? because you have a bar, okay, and then you apply very simple force at both ends. So you don't care much about the traction that you apply, but you care about the net force, and the net force here is very simple, right? You have only one component of the net force at both ends and no net moments at all, okay? So this kind of problem, I think that is simple enough. So I will guess the solution, okay? So I will get the I will get straight field, okay? Because it's quite simple in my opinion. I can use the knowledge from undergraduate class at the starting point. Okay, you may go back and try to solve this problem by guessing the displacement field. That is one way that you can do. But here I think it's simpler if I guess the solution in terms of straight field, because you learn from you have the knowledge in string material class before. You know that okay, straight should be POA, right? That's what you learn from that class. Is that right? And we know that okay, for this case, in the sense of string material class or solid or mechanical material class that you took before. So in that class, you know that okay, apply the force like this, there's no shear stress developed inside, right? There's only normal stress in x3 direction. Sigma 1, 1 and sigma 2, 2 should be 0, right? And sigma 1, 2, sigma 2, 3, sigma 1, 3 should be 0. So we have only sigma 3, 3 here, right? That is based on the knowledge from string material class. So now I guess straight field like this. Okay, I don't know exactly here that this is correct, but it's the first choice that I can think about. I can come up with this one based on the thing that I learned from string material class, right? This is the best that I think I can think about. Is that how about you guys? If I ask you to get the solution of this problem, will you come up with the same as what I got here? So it depends on your experience. And if you understand the problem clearly, you may come up with the solution that I guess here, right? Up to this point, I don't know exactly. I cannot say that okay, the one that I guess here is the right one. Okay, because here we try to solve the problem in different context. Okay, we try to verify the simplified boundary value problem that we and I put before, right? Okay. I guess I start by guessing straight in this particular form. If I check everything and if they are satisfied, now I can confirm that this one is the right solution. If I cannot satisfy all the conditions that I need, I have to come back and modify the guessing, the guess straight field, right? Okay. Stress that I guess here is simply P over A for the component sigma 3, 3, right? The rest is 0. Okay. So A here is a cross-sectional area. Okay. I don't care about the shape. It can be of any shape, right? It can be arbitrary. Okay. How can we verify the given straight field here or the guess straight field here? You can go back and look at the lecture that I gave you before, right? Okay. So if you start by guessing straight field, now you have to check equilibrium, right? So I check equilibrium. Okay, and it's quite clear here because the body force field is 0, right? So the body force B is 0 for this case. And also stress that I guess here is constant. It doesn't depend on X. So if you look at equilibrium equation, they should be satisfied automatically, right? Because B is 0 and sigma ij is constant. So this equation is satisfied. Okay, now I check equilibrium. Next, we have to check that, okay, straight field can provide the displacement field, or straight field have to be compatible, or it have to generate strain that's compatible. How can we check that kind of condition? You see, it's very simple. I showed you before, right? So you can check Beltrami-Michel equation directly, because Beltrami-Michel equation are conditioned to confirm the compatibility of strain in terms of stress. Okay, so this is the Beltrami-Michel equation for the case that body force is 0. So term on the right hand side that involve B just disappear here. Okay, so now I just simply plug in straight field that I have, okay, for this particular case. You can see that straight field that I get is constant. Term on the left hand side of Beltrami-Michel equation involve the derivative of the function with respect to the coordinate, right? So because straight is constant, so this term disappear and that term disappear. So now I can say that this equation is satisfied, right? Automatically. Okay. So now what we can conclude here is that if we assume stress to be constant, as what I showed you before, the governing equation inside are satisfied, right? Because we need to check only two types of the governing equation. One is the equilibrium of straight field, and the second one is the compatibility condition through Beltrami-Michel equations. Once these two are satisfied, now I can say that we can generate all the field inside, right? We can generate strain field easily by simply using strain displacement relationship. We can get displacement easily by, not easily, I shouldn't say easily, because displacement field, you have to perform the integration, right? To get displacement field, it takes some time, right, for that. Okay, so now I can generate all the field. The rest that I have to verify is the boundary conditions. One question that may arise, should I get strain and displacement field first, or should I verify traction first? Should I verify the boundary condition first for this case? Because we are not sure yet that stress that we get is a solution or not. But in this problem, we don't have displacement boundary conditions, right? So there is no need to get displacement first, right? Because displacement will not be used to verify the boundary condition. Then in this case, I will check the boundary condition first. Once the boundary condition are satisfied, now I confirm the choice of stress, and then I can get strain and displacement if you want. Okay. How can verify the boundary conditions? I will start looking at the boundary condition at the surface S pi. If you go back and look at the simplified BVP, we didn't modify anything on the boundary condition for the surface S pi. We still need to check the traction at every point on the surface S pi, or I can say that the original boundary condition on the surface S pi have to be satisfied. Okay, the only thing that we modify is at the left and at the right end. So we expect that, okay, the straight field that we gave there satisfy the boundary condition on the surface S pi at every point. Okay, I will show you here. Okay, so on the surface S pi, we can generate traction from the gauge straight field. It should be very simple, right? We just simply multiply the gauge straight field, which is constant like that, and we multiply by the normal vector. The normal vector to the side face, because the body here is cylinder. Okay, so the normal vector should be what? The normal vector at every point on the side face here. N here, because the cross section is of arbitrary. So n1 and n2, the component of n here in 1 and 2 direction can be anything. But the component in x3 direction is 0. Because if you remember, the geometry of the body here is cylindrical geometry, right? So the cross section is of the same. It's the same for any part here that normal to the axis x3. So in that case, you can see that n have 0 component along x3 direction. Okay, is that clear to you? So if that is the case, when I multiply straight field that I guess with this normal vector on the side face, I always get 0, right? Is that right? It doesn't matter the value of P and A are, right? So this always give you 0. What does it mean? And this is the one that we got from the case straight field. And look at the one that we have here. So the traction that prescribed on the side face is also 0. Is that right? So now what we can conclude? We can say that the boundary condition on the surface S pari are satisfied automatically for the case straight field. It doesn't depend on the choice of P and A. Okay, P and A can be anything, right? So this condition is always satisfied, right? Okay, so the case straight field here at least satisfy the side face conditions. Next time, I will come back and finish the rest of this problem. Okay, it still remains to confirm the condition at the left and at the right end. Okay, we need to confirm that the condition at the left and at the right end are satisfied. And I will show you next time that, okay, the condition at the left and at the right end, I will not force the traction to be satisfied anymore. I will force the net forces and moments to be satisfied instead. Okay, I will stop here. Do you have any question about anything?มีคำถามอะไรไหมครับ Okay, if you don't have any question, so I will
อาจารย์ครับ
ครับ
สมมุติว่าถ้าบอดี้มัน symmetry อย่างเมื่อกี้ครับสมมุติว่าถ้ามันเป็นมี traction ที่เป็นดึง tension สองข้างแล้วมันสมมาตรกันอย่างเงี้ยครับมันมีถ้าเป็นวัสดุถ้ามันเป็น linearly isotropic อย่างนั้นนะครับ boundary condition มันมีตรงกลางที่บอกว่าจุดตรงกลางจะไม่มีการยืดหดไหมครับอาจารย์อันนี้สามารถมองได้ไหมครับอาจารย์
ไม่เข้าใจคำถามคุณเลยอ่ะมันเกี่ยวอะไรกับปัญหาที่เราซฟตรงนี้หรือเปล่าคือผมยังนึกไม่ออกว่ามันเกี่ยวข้องอะไรกับปัญหาของเรานะอีกทีดิ
คล้ายๆกับมันเป็นตัวในการบ้านนะครับอาจารย์
คุณกำลังถามการบ้านหรือถามปัญหานี้
ไม่ใช่ครับคนละคำถามกันครับแต่ว่าอันนี้มันก็สมมาตรเหมือนกันนะครับอาจารย์
อันนี้ไม่สมมาตรครับตรงไหนสมมาตรหรอคุณพูดถึงอะไรสมมาตรบอดี้ไม่สมมาตรเนาะ
ไม่ใช่ครับแรงที่กระทำ traction ที่กระทำกับ
มันก็ไม่ได้สมมาตรแล้วมันมีประเด็นอะไรนะเดี๋ยวผมนึกไม่ออกว่าคือคุณกำลังจะสื่ออะไรอ่ะต้องถามผมอีกทีดิคือสิ่งที่คุณต้องการจะสรุปคืออะไรอ่ะ
อยากรู้ว่าที่ตรงกลางกึ่งกลางของตัวบอดี้เนี่ยครับมันจะมีเราสามารถบอกได้ไหมว่า u ในทิศทาง x3 เนี่ย u3 ตรงจุดกึ่งกลางเนี่ยจะเป็น0ถ้าเป็นlinearly
ง่ายๆคือแล้วทำไมเราต้องใช้ตรงนั้นน่ะเพื่อ
สมมุติว่าเวลา solve ตัว boundary value problem
คุณโซฟ boundary value problem คุณก็ดูที่ boundary สิไอ้ตรงจุดที่คุณพูดถึงอยู่ที่ boundary ปะถ้าไม่อยู่คุณจะใช้ได้ไงอ่ะมันเป็น condition ที่ผมไม่เคยอธิบายคุณนี่นะไม่เคยให้คุณใช้เลยนี่เนาะใช่ไหม ถ้าคุณจะใช้นั้นแสดงว่าคุณต้องพิจารณาบอดี้ใหม่สิคือถ้าเกิดคุณจะใช้ความสมมาตรคุณก็ต้องตัดตรงกึ่งกลางนั้นน่ะเหรอแล้วออกไปอย่างเงี้ยเหรอเราคิดครึ่งเดียวอะไรเงี้ยเหรอถ้าเกิดคุณไม่คิดอย่างนั้นคืออย่างง่ายๆถ้าคุณจะหาคำตอบของปัญหาเนี้ยปัญหาอะไรก็แล้วแต่เนี่ยคุณต้องสอดคล้องเงื่อนไขอยู่สองส่วนหนึ่งก็คือสอดคล้องสมการข้างในอีกส่วนหนึ่งคือสอดคล้องเงื่อนไขขอบเขตถ้าผมบอกสองอันนี้ที่คุณจะต้องสอดคล้องถามคำถามก็กลับไปว่าไอ้ที่คุณกำลังจะทำเนี่ยคุณกำลังทำในส่วนไหนในสองส่วนนี้หรอถ้าเป็นอะไรที่นอกเหนือจากสองส่วนนี้ก็ถือว่าทำไม่ได้ไหมยกเว้นคุณจะ modify body คุณถ้าคุณจะซฟปัญหาคุณเต็มคุณก็ต้องพิจารณาการสอดคล้องเงื่อนไขของสมการข้างในกับเงื่อนไขขอบเขตแค่นั้นครับผมยังนึกไม่ออกว่าทำไมต้องทำอย่างที่คุณบอกเพราะถ้าเกิดคุณไปทำตรงนั้นนั่นแสดงว่าคุณกำลังสมมุติอะไรที่อาจจะไม่จริงก็ได้โอเคถ้าเกิดคุณแน่ใจมันต้องถามก่อนว่าถ้าเกิดคุณบอกว่าคุณคิดว่ามันสมมาตรเนี่ยคุณแน่ใจเหรอว่ามันสมมาตรจริงมันมีบริจิต body motion ได้ไหมสมมติว่าง่ายๆว่าผมมองปัญหาเนี้ยถ้าคุณบอกว่าเฮ้ยไอ้ cross section ตรงกลางเนี่ยมันควรจะอยู่นิ่งๆใช่ไหมมันจริงเหรอก็ในเมื่อ displacement มันเกิดยังไงก็ได้อย่าลืมว่าเรามี rigid body movement ได้ในกรณีที่ body เราไม่ได้ restrain กับการเคลื่อนที่เลยเนี่ยอย่างรูปเนี้ยคุณบอกได้ไหมว่า cross section ตรงเนี้ยตรงกลางเนี่ยมันไม่เคลื่อนที่คุณรู้ได้ยังไงใช่ป่ะมันเคลื่อนที่ได้เนี่ยคุณหมุนมันก็ยังได้เลยอันเนี้ยเพราะมันไม่มีเราไม่ได้ specify displacement เพราะฉะนั้นคืออะไรก็ตามเงื่อนไขอะไรก็ตามที่เรากำหนดขึ้นมาเนี่ยเราต้องถามก่อนว่ามันจริงหรือเปล่าเราชัวร์เหรอแล้วอีกอย่างคือการที่สมมุติจุดอะไรข้างในมันขัดกับสิ่งที่ผมสอนคุณป่ะถ้าเกิดคุณจะเปลี่ยนจุดข้างในมาเป็นบาร์รี่คุณก็ต้องตัดมันครึ่งหนึ่งเนี่ยคุณบอกคิดครึ่งหนึ่งแล้วคุณก็บอกว่าตอนเนี้ยคุณก็จะฟอร์สไอ้คอนดิชันตรงจุดที่คุณกึ่งกลางที่คุณตัดเนี่ยอย่างนั้นโอเคแต่ว่าคุณต้องมั่นใจนะว่าการตัดแบบนั้นไม่ทำให้อะไรเปลี่ยนแปลงถ้าเกิดคุณจะโซฟปัญหาคำตอบของปัญหาเริ่มต้นเลยที่คุณไม่ได้ modify รูปร่างของไอ้ตัวที่คุณมีอยู่คุณไม่ได้ตัดมันเอาคิดแค่ครึ่งเดียวอะไรอย่างเงี้ยก็ใช้อย่างที่ผมบอกคุณก็สอดคล้องเงื่อนไขของสมการกำกับภายในแล้วก็สอดคล้องเงื่อนไขขอบเขตที่ทุกจุดครับตามนั้นเลยคือไอ้สิ่งที่คุณบอกผมมาเนี่ยผมว่ามันสุ่มเสี่ยงนะที่คุณอาจจะสุดท้ายคุณจะได้คำตอบเหมือนกับที่เพื่อนคุณได้ก็ได้ที่ทำวิธีปกติที่ผมสอนแต่ว่ามันมีโอกาสเป็นไปได้สูงที่มันอาจจะไม่จริงก็ได้เพราะว่าถ้าเกิดคุณมีปัญหาที่เป็น rigid body motion ร่วมอยู่ด้วยเนี่ยมันจะไม่จริงแล้วและอีกอย่างคือการที่เราสมมุติเรื่อง symmetry เนี่ยคุณก็ต้องระวังด้วยว่ามัน symmetry จริงหรือเปล่าใช่ไหมการที่มันจะ symmetry เนี่ยมันจะสมมาตรเนี่ยต้องสมมาตรทุกอย่างจริงๆนะแม้กระทั่งเงื่อนไขเรื่องเกี่ยวกับการเคลื่อนที่แบบ rigid body motion ด้วย
โอเคครับอาจารย์ขอบคุณมากครับ
ผมอาจจะไม่เข้าใจประเด็นของคุณคือคุณกำลังจะทำอย่างนั้นเพื่ออะไรนะถ้าทำปกติมันหาคำตอบไม่ได้เหรอหรือไง
อย่างสมมุติว่าถ้าเราต้องการจะโซลฟพวกตัว A ตัว rigid body motion อย่างเงี้ยครับอาจารย์
แล้วคุณโซลฟมันได้ปะล่ะเพราะถ้าเกิดคุณกำหนดอะไรขึ้นมาเนี่ยที่มันไม่ได้เป็นจริงคุณรู้ได้ไงมันจริงปะล่ะถ้าคือการจะโซลฟ rigid body motion ผมก็บอกไปแล้วคือการที่คุณบอกว่าคุณจะหาไอตัว A จากการอินดิเกตคุณอินดิเกตเสร็จสมมติคุณอินดิเกตเสร็จแล้วหรือไม่กระทั่งคุณ assume displacement เนี่ยการที่คุณจะหาค่าคงที่พวกนั้นได้มันก็ต้องอาศัยเงื่อนไขขอบเขตปะเพราะฉะนั้นถ้าเกิดคุณบอกว่า body คุณมันถูกป้องกันการขยับในบางจุดเนี่ยคุณก็เอาจุดพวกนั้นคุณก็เอาส่วนพวกนั้นมาหา A ไม่ได้หรอหา A หา B อะไรที่คุณต้องการจะหาก็ได้นี่ทำไมต้องไปหาใช้จุดตรงกลางด้วยไม่จำเป็นมั้งถ้ามันหาไม่ได้ก็ต้องหาไม่ได้คือผมไม่ได้บอกว่ามันต้องหาได้ทุกตัวนะเพราะฉะนั้นคุณต้องบอกว่าโซลูชันที่คุณได้มามันสรุปอะไรได้บ้างมันยูนิคไม่ยูนิคยังไงมันก็อย่างที่ผมเคยบอกว่าdisplacement มันไม่จำเป็นต้องยูนิคไงถ้าเกิดมันไม่ปัญหาของคุณยูนิคก็ล่ะถ้ายูนิคคุณก็ยูนิคถ้าไม่ยูนิคก็ไม่ยูนิคมันเป็นไม่ได้ไงถ้าไม่ยูนิคก็แสดงว่ามีrigid body motion ได้แล้วคราวนี้บางตัวของไอตัวค่าคงที่เกี่ยวข้องกับ rigid body motion บางตัวจะหาได้ก็ได้ เพราะคุณอาจจะป้องกัน rigid body motion ในบางทิศทางไปแล้วซึ่งตรงนั้นเนี่ยแนะนำว่าให้ทำผ่าน boundary condition คุณจะไปกำหนดจุดขึ้นมาบางจุดแล้วบอกว่าตรงนั้นเนี่ย displacement เป็น0อย่างเงี้ยในบางทิศทางเนี่ยมันจริงหรือเปล่าล่ะด้วย boundary condition ที่ผมให้คุณไปมันเป็นอย่างนั้นจริงไหมถ้าไม่จริงก็ไม่ควรมันไม่สามารถกำหนดได้นะใช่ไหมโดยเฉพาะจุดข้างในจุดข้างในเนี่ยคุณไปกำหนดว่าจุดข้างใน body มันมี condition เป็นแบบนี้แบบนั้นมันไม่ได้เพราะว่าถ้าคุณลองกลับไปดูที่ boundary value problem ที่ผมเซตอัพตั้งแต่ต้นเนี่ยคุณก็เห็นชัดเจนอยู่แล้วว่าเราจะไม่ได้กำหนดค่าอะไรข้างในเลยใช่ปะจุดข้างในเนี่ยเราต้องสอดคล้องสมการกำกับแต่จุดที่ผิวเราจะสอดคล้องเงื่อนไขของค่า traction หรือไม่ก็ displacement ขึ้นอยู่ว่าเรารู้อะไรก็ใช้แค่นั้นเองครับนะการฟอร์สค่าของการเคลื่อนที่ที่บางตำแหน่งโดยที่คุณไม่มีเงื่อนไขนั้นจริงๆเนี่ยต้องถามก่อนว่าเหตุผลที่ทำงั้นเพราะอะไร
โอเคครับอาจารย์ขอบคุณมากครับ
โอเคเราเข้าใจประเด็นไหมเข้าใจประเด็นเนาะ
เข้าใจครับเข้าใจ
โอเคมีคำถามอื่นไหมyour friend just asked me about the homework okay he asked me about how to get the the rigid body motion part in your homework I didn't say that the displacement is unique okay you have to think about that because the problem that you have to deal with in the homework assignment you have to deal with the mixed condition on the battery right so you have part of the battery that you know traction and part of the battery that you know displacement right and some of the some component of the traction and some component of the displacement are known right at the same point so this kind of mixed condition you have to check okay I cannot tell you here that okay the displacement finally have to be unique or not okay it depends on the body that you look at if you look at the way that I constrain the body you should if you have the common sense you should know that okay the body that you have to solve here the body that you have to focus on here can experience some of the rigid body motion or not for example it can slide in one direction freely or not so that is the common sense that you can get it from the picture that I gave you but when you try to verify the solution you come up with something that consistent with your common sense for example if I have the body that can experience the rigid translation in x1 direction for example so now when you solve the problem and you verify all the condition there will be one constant left in u1 the constant that left in U1 will represent the rigid movement or rigid translation in x1 direction. So they have to be consistent in that way. Okay. So to get all the constants, you need to enforce the boundary condition at every point. You cannot just simply verify at some particular points. For example, if you look at one phase, you know that the displacement U1 on that phase equal to 0 at every point. Now you have to make sure that okay that condition is satisfied at every point. Okay, if you confirm only some particular point, that may not be enough. You know what I mean, right? Make sure that okay when you choose points to verify or to determine all the constant, the condition there once you get once you get the constant, the condition at every point on that phase are satisfied as well. Okay, I know that okay because you have a finite number of constants, but you have infinite number of points on the phase. So if you try to force the condition at every point, you may have a lot of equation to deal with, but those equation may not be independent. Okay. May not be independent. So one way that I suggest you to do, try to go back and take a look at the linear independence that you learned from Ajahn Chatpan. That will help you to conclude things when you try to satisfy the condition at every point on the phase. what can you conclude when some of the coordinate there are arbitrary, right? Because it can be any value on that phrase. So if some of the coordinate there are arbitrary, what can you conclude from that condition? For example, if I say that ax1 plus bx2 is always equal to 0 on that surface when x1 and x2 can be anything. For example, in that way, so now you can say something on the constant, right? In front of the coefficient of x1 and x2. Try to use the linear independence of x1 and x2 and arbitrate of x1 and x2. So that will conclude, for example, I have ax1 plus bx2 equal to 0. If this equation if this condition is satisfied for every x1, x2, now I can say that a and b should be 0, right? If a and b cannot be 0, this condition cannot be satisfied at every x1 and x2, right? This kind of procedure should be used in your homework assignment. Okay, so I don't suggest you to just simply pick a point and satisfy some condition without looking at the the satisfaction of the boundary condition at every point on the surface. If you want to do in that way by setting some of the condition to get enough equation to solve for constants, but you need to go back once you're done with that constant, you get that constant. Can you check it again that okay, with that set of constant, you satisfy everything on that phase? Okay. Okay. มีคำถามอะไรเพิ่มเติมไหม Okay, if you don't have any more questions, so I will stop here. I will see you guys again on this Thursday, okay? Don't forget that we will have the exam on Friday, okay? So the exam will start at 9, okay? So it's a closed book exam. So prepare yourself ready for the exam, okay? If you have any question about the materials that we'll cover in the exam, you can always ask me. Okay, feel free to ask me anything related to the materials that I cover. Okay, I will see you again on Thursday. Have a good day.
Thank you อาจารย์
Bye bye.
สวัสดีครับ
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 สวัสดีค่ะ